So we're taking a look in this PowerPoint at how to evaluate sums. There's not a lot of calculus involved in what you're doing here. It's really more about notation and understanding what the symbols mean. Okay, so now the reason we're looking at this is that we're going to be using this as a foundation for really what we do in Chapter 5. And the introduction to this module kind of goes through that. If you read any of what was posted right above the link here, we talk about why this is important. Okay, so what we're going to do here is talk about the how, and then as we go throughout the next few videos, you'll see why this is important and how it takes shape. So let's look at this slide here. The Greek capital letter sigma is used to express long sums of values. Okay, so if you look at this, you see that we've got sigma, okay, and the a sub I, and I equal to 1 indicates where we're going to begin this long sum, and n indicates where we're going to end. Okay, so this will make sense a little more as we go throughout this PowerPoint. We call I the index, and if you look, each term is evaluated beginning with the value when I is 1 and ending when I is equal to n. Okay, so if you had an expression that looked like this, I equals 2 to 7, we would have sum 2 plus 3 plus 4 plus... So I indicates which term we're going to begin with and which term we're going to end with. Note that the index is only used to keep track of the terms. It does not factor into the calculation. Okay, so it's a dummy variable, so to speak. If we have A1, A2, and AN, and B1, B2, Bn represent two sequences, the following properties are going to hold true. So you take a look at this, right? If you go back, C right here was a constant. So if we're trying to find the sum of a constant from the first or the ith term to the nth term, then that sum is just going to equal n, whatever this n is, times that constant. We're going to work with each of these properties as we go throughout this page or this PowerPoint. Here we have a constant times a sub I. And a sub I and b sub I are going to represent, they may represent expressions. For example, a sub I might equal something like x plus 3, okay? We're going to do an example here in a minute where we have an exclamation point. So you'll see how that works. So right here we've got, given that we have the sum from 1 to 100 of b sub I equal to 15. Okay? Compute this thing right here, okay? 3 minus 4 b sub I. So remember what we said about b sub, the sum from 1 to 100 of b sub I is 15. So we're going to take this and break it up using those properties. So I'm going to break this up, and I'm going to have the sum from 1 to 100 of 3, that's a constant, right? Minus 4 times the sum from 1 to 100 of b sub I. Now we've already said that this is equal to 15, right? We made that notation up here. So the big question is, where does this 3 times 100 come from? If you recall, one of our properties was this, right? It was that thing right there. It's equal to whatever n is times this constant. So here we have 3 times 100. So to figure this out, I'm going to do 300 minus 4 times 15 is 60, and that gives us a sum of 240. So if you're not quite understanding about this sum thing, you're going to see that play out here in a little while. So let's take a look at this one. This is just very similar to what we just finished doing. This time we have the sum from 1 to 45 of A plus the sum from 46 to 100 of A. And again, we're going to use those properties that we talked about earlier. This one we're using the property where we have, I keep doing that n, it's I equals 1 to 100 of A. That is n times A, right? If we go back and look at that, or C, in this case, C times A, right? So I'm going to go in and I'm going to say, since A is a constant, right? We were given that a is a constant right here. We're just going to have 3/4 times 100, or 75. So what we're doing is we're taking this idea, right, and we're rewriting those two sums as one sum. So notice we go from 1 to 45 and then 46 to 100. So we could combine these two into just one sum from I equal 1 to 100 of this constant. And we said before that if we have this this sum here, it's just going to be 3/4 times whatever n is right there. So if I have the sum of n integers, okay, where we have the sum of n integers, right? This is the first one plus the next number is 2 plus so and so until we get to n, all right? There's a formula that we learned in some of our high school math classes for this, and it's this thing. It's n times n plus 1 over 2. So if I just want to sum the first 50 integers, I would do 50 times 49 divided by 2. Okay? Here's one where we have the sum of consecutive integers squared and the sum of consecutive integers cubed. So we have these different formulas that we're looking at as we go throughout these different sums here. Here's one where I have the sum from 19, 20, 21, all the way up to 42. Okay, so these are integers, right? These are just regular old integers. And we talked about how to do that just momentarily ago. We're going to take the sum from 19, that's where we start, up to 42 of these integers. And if you remember, we talked about how we could do 1 to 42 minus 1 to 18. So where on earth are we getting this? Remember, we have 19 to 42. So I could say it like this. I could say I equals 1 to 19 plus the sum from 20 to 42, right? We could write it like that, or maybe better yet, in terms of what we have here, we could say, because we've got the sum from 19 to 42, we could say from 1 to 18 plus 19 to 42, right? If I write those two sums, I know it's going to equal the sum from 1 to 42. Okay, so we do a little algebra here and we isolate this thing by subtracting that from both sides. Well, why on earth would we do that, Mr. Starr? Why would that even make sense? Well, if you look, we gave you a formula for finding the sum of the first few integers, right? So we're going to apply this thing to what we have here, right? I've got, and it's important that we apply this formula when I equals 1, because that's what our formula had. If we go back and look right up here, our formula has I equal 1 to n. So this section, again, is all about notation. So I'm going to have 42 plus 1. I think I gave you incorrect. I think I did 49 here. It should have been 51. Apologize. So 42 times 42 plus 1 over 2 minus, if you notice, we end with 18 and we begin with 1. 18 times 18 plus 1 over 2. So 42 plus 1 is 43. And if I multiply those together, divide by 2, I get 903. Multiply 18 times 19, divide by 2, I get 171. So the sum of those, right, the sum beginning at 19 and going to 42 of these integers is going to be 732. In other words, if I add 19, 20, 21 on the calculator, if I keep doing this all the way up to 42, I would get that number right there. Well, summing a problem that looks like this is going to work real similar. Let's think about what we did in that last problem. So I would want to go from I equals 1 to 7 plus I equals 8 up to 18. And that would allow me to find the sum from I equals 1 up to 18, right? So we're using those properties that we talked about. We can isolate this term here. If I move this guy to the other side, that's where that subtraction comes from. And if you notice, you'll see how the square comes into play. So if I do the sum from 1 to 18, it would look like this. 18 times 18 plus 1 over 2. And then 2 times 18 plus 1 over 6 here. So we're getting this information from our property right here, right, where we have I squared. Notice they gave me that formula there that I want to use when I do this problem. So I'm doing 2 of those. I'm doing 1 for the 1 to 18 term and 1 for the 1 to 7 term. The one I wanted to show you is going to look like this, and you're going to see this in the homework for Newton here. And it says find the sum, and this time they use K. So we don't always use I, but occasionally we'll see some other letters here. And this one is -3 over K exclamation mark. So I wanted to show you this one because we don't do one like this in the PowerPoint. I don't want it to surprise you. And I want to really stress to you what we mean when we say sigma, when we talk about the sum. So I'm going to begin by finding out what -3 over 2 is, 2 factorial. This is known as factorial, and you may have seen it in some of your other math classes. This may be new for others of you. Plus -3 times 3 factorial, plus -3 times 4 factorial, plus -3 times 5 factorial. So we're going to have a bunch of negative numbers that we're combining. And then I'm going to go in and say, well, -3 over 2 factorial. Well, 2 factorial is simply 2 times 1, or 2. Plus -3 times, or -3 over 3 times 2 times 1. Well, that's 6. Plus -3 over 4 times 3 times 2 times 1. Well, 4 times 3 times 2 times 1 is just going to be 4 times 3 factorial, right? 4 times 3 times 2 times 1. I already know that 3 factorial is 6, and if I multiply that by 4, I get 24. And then I'm going to throw in -3 over 5 times 24. That's 120, okay? Now, here's the thing. You've got to add these together. You've got to get a common denominator. And it turns out that 120 is going to be that common denominator. So I'm going to have this thing, 24, I'm going to multiply that by 5 and that by 5. Here I'm going to multiply 6 times 20 and 3 times 20. And then this last guy I'm going to multiply by, 60 and 60. So my common denominator is going to be 120, and up top I'm going to have -180 minus 60 minus 15 minus 3. If I combine all of that together, I'm going to get that final answer. Let me get my calculator here. So 180, and I just want to do my calculator so that I make sure I don't make any mistakes. So I make sure I don't miss this one. All right, so I did this twice. I got a second answer thing and 3. Yeah, 258. So I get -258 over 120. So having that calculator handy is something you might want to make sure you've got. I'm going to look to see if I can simplify that. And both of these numbers are divisible by 6. So I get -43 over 20. I can't reduce that one anymore. That's going to be my final answer, -43 over 20. So again, this exclamation point is new for some of you, right? It's not 2, right? It's just 2 times 1. Here, this is 3 times 2 times 1. This is 4 times 3 times 2 times 1. And then 5 times 4 times 3 times 2 times, squeeze it in there, 1, okay? You want to make sure you get in and get these done. Let me know if you have questions. I want to make sure that anything you're seeing in Newton that you haven't seen before, let me know so that I can go in and add to the student experience. I want to try to I want to try to leave enough for you to do some discovery on your own, but at the same time, I don't want you out there floundering. So please let me know if there's anything, any additional resources you feel like you need, or anything you're not getting. If we review this, right, the big point here, the big thing we want to get across is this symbol right here means that we are adding a bunch of things together. You saw how that plays into what we're doing here in the introduction to this section. You keep reading, keep working through these sections, and you're going to see how this sigma plays an even bigger part in the next two sections.